In the last segment in this ZeroMQ Python MetaTrader series, we discussed trade execution, reporting, and management via ZeroMQ between Python and MetaTrader. Today, we're going to discuss how to subscribe to market data, again via ZeroMQ between Python and MetaTrader. However, Python isn't necessarily the only external environment, only external programming language that can be employed here. Any ZeroMQ supported programming language can be used here to achieve exactly the same functionality or more. In terms of prerequisites, again, the prerequisites remain the same from our last tutorial on this: programming experience in the following languages: C, C#, C++, Python, R, and definitely MQL. You don't necessarily have to have experience in all of the aforementioned languages, but one of them at least, and MQL would be good for the purposes of following this content. Trading experience with MetaTrader 4 and or 5. Knowledge of certain MQL EA functions is a plus, but is optional for this tutorial. And some MetaTrader terminology is, I would consider, essential for following the content successfully. Again, those include lot size, magic number, ticket, order types, etc. In terms of agenda today, we'll continue straight on from where we were last time. We did a brief demonstration on how to subscribe to market data using the Python script supplied in the DWX-ZeroMQ-Connector directory on GitHub. Today, we're going to take it a step further and discuss how to set up a MetaTrader market price server using ZeroMQ as the bridge between your external programming environment and MetaTrader. Again, if you haven't watched the first two, the first webinar and the second tutorial video, those being how to interface Python R with MetaTrader 4, and the second being a tutorial video on trade execution, reporting, and management with MetaTrader 4, it is strongly advised that you watch those prior to continuing with this series. However, that is not strictly mandatory. It would, however, be very, very helpful if you did. We'll continue on from demonstrating how to set up a market price server to discussing a topic that is often considered difficult to approach, which is MetaTrader's HST file format. We're going to demystify that for viewers, show you users how simple it is, in fact, to obtain data from the HST archives inside the MetaTrader root directory, and how you can perform lookups on the HST archives for data on demand. We'll talk a little bit about efficient data lookup from HST archives, since they are flat files, and a few ways to do so. Plus, we'll ask you for any of your inputs and feedback on the same that you'd like to share, and that we can possibly use to engineer the most efficient solution possible to extracting data from HST archives on demand. And then we'll talk a bit about what comes after this tutorial. So let's begin. The very first thing we're going to do is, again, as we did before in the last segment, switch straight over to our environments, those being Python and MetaTrader, and make this an interactive, hands-on tutorial. So now we're going to switch to So here we are in my Spider IDE, and we've got the script loaded up as we had last time. No changes have been made other than minor code changes that don't affect functionality, and all these changes have, of course, been committed to the file on GitHub as well. First thing we'll do is load the script so we can create our instance of the DWX-ZeroMQ-Connector class. We're going to do some things slightly differently today. Our objective is going to be to use one MetaTrader terminal as our price server and keep it for that purpose only. We're not going to use it as our terminal for executing trades, managing and reporting, as well as publishing prices from MetaTrader for any number of symbols that we choose. So now that the script has been loaded, we'll first create our DWX-ZeroMQ object, the connector bridge object, and specify a different subscriber port than we did last time. The reason for this being that we want to use one terminal for one purpose, that purpose being to serve as our price feed server. For any trading instructions, reporting and management related functionality, ideally we want to use a separate MetaTrader for terminal altogether for that. Reasons for those vary, but the most important reason there being that we don't want to overload MetaTrader with too many things all at once. Trade execution is a sensitive subject. It's something that should be handled cautiously, and to avoid any sort of hang-ups or any other scenarios that may affect MetaTrader as a result of both processes, trade execution, management reporting, as well as market price subscription happening on the same terminal, we'll play it safe and use a dedicated terminal for price feed, for serving price feeds, and a dedicated terminal for employing trade execution, reporting, and management. Today we're focusing just on the former, which is market price subscription. The default port is 32770 in both the Expert Advisor as well as the script. We're going to change it just slightly and specify 32771 as our subscriber port, and we'll change it accordingly in our dedicated price feed terminal that I'm going to pull up shortly. That's the only change we need to make for this demonstration. We're going to go ahead and create the instance with that. So our ZMQ instance is ready. The next thing we need to do is make sure our MetaTrader terminal is listening, is publishing prices for all symbols available as selected in our script to that port, so that this ZeroMQ script can subscribe to it on that port. Let's switch over to our MetaTrader terminal. As before, we have our demo account loaded for demonstration purposes, and the first thing we're going to do is load the Expert Advisor onto our chart, making sure we make that port change prior to executing it. So we'll drag the Expert Advisor on as we did before, change the publish port here to 32771 so that it matches the subscribe port in our script, and set publish_market data to true. Now you can see that the default symbols in the script provided as is, MetaTrader has already started publishing bid-ask data for them. Let's go have a look at what those symbols are. They don't have an input parameter in the EA's input settings, but they are visible if you go through to the code itself, where in the first few lines you'll see we'll see the symbols that MetaTrader by default will publish information for. These are 7. You can add as many as your MetaTrader terminal and resources will support. So feel free to change this accordingly, making sure that when you do change the number of entries inside the array, that you change the size of the array accordingly. Just a little programming note there for you. Going back to our MetaTrader terminal, in here we see that MetaTrader is publishing prices for the assets we just saw in the script to port 32771. Going back to our Python script, we're now able to subscribe to those prices by symbol. So MetaTrader is publishing that information by symbol, and all we need to do here to set up our feed coming into our Python environment is to subscribe to our symbol of choice. That symbol must be in the list of symbols that MetaTrader is publishing information for from the terminal. So we'll go here to _ZMQ._DWX, scroll down to subscribe market data, and specify the symbol we'd like to subscribe to data for. In our case, let's subscribe to a few. So let's go subscribe to EURUSD as we did in the last segment. We're now subscribed to EURUSD. Let's make sure that that is indeed happening in the background. So to do that, by default, this script will save all inbound price data into a variable called market data DB, which is a dictionary object, keys of which contain information sent to this script by MetaTrader, or well, the information that this script has subscribed to from MetaTrader that is publishing that information. If we take a look at the keys of this dictionary, we'll see that EURUSD is one of them, which implies that either EURUSD is a symbol that this script is currently subscribed to or was subscribed to at some point and has data available for. To view this data, we simply go back and specify the key, and that is simply done by entering the name of the symbol we subscribed for. You'll see that this information is being published by MetaTrader, and in MetaTrader we see this information in the Experts tab for each symbol that has been specified in the script for MetaTrader to send bid-ask data to the publish socket for. Going back to the Python environment, let's try and subscribe to some more symbols. So let's go again. Same command, DWX subscribe market data. This time let's subscribe to something different. Let's subscribe to the dollar yen. And now we're subscribed to two symbols. Let's take a look at the keys. You'll see that dollar yen has entered the keys list. And to view the dollar yen data, we simply need to go back to our internal variable called market data DB, specify dollar yen, and see that dollar yen prices are now being passed from MetaTrader to the Python environment as well. And they will keep growing as data comes in. Anytime you want to unsubscribe from one or more of these, as we mentioned in the last video, we have functions available to perform that unsubscription a symbol at a time or en masse. So in the last video, I showed you how to unsubscribe from a single symbol, which was via the unsubscribe market data request, which accepts a single parameter of the symbol. As we've already done that, I'd like to show you what the mass unsubscription does, which is very simply just unsubscribes you from all the symbols that you've sent market subscription requests for to MetaTrader. And that is DWX, MTX unsubscribe, or market data requests. We go over there and we don't need to provide any information. It simply looks at the keys and starts unsubscribing the script from MetaTrader's publications immediately. And now all symbols that had been subscribed to before have been deactivated. So data for those symbols will still be available inside the same ZMQ._market data thread, a market data DB object. But no more data will be added to this dictionary because we've effectively unsubscribed from any subscriptions we made before. In this manner, what we've effectively done is done are two things. Firstly, we've instructed MetaTrader to act as our price feed server. In order for us to change the composition of symbols, it's a case of at the present time, it's a case of modifying the code and adding the appropriate symbols as necessary. An input parameter was for these was sort of lazily avoided at this point in time, as it could become a fairly large input parameter in terms of the space it occupies in the input screen. If you, for example, enter a fair few more than 7 pairs here or assets here. So at the present time, this is available inside the script. All you need to do here is simply add or remove assets from this list, and making sure that however many you add or remove, that you adjust the size of the published symbols array accordingly, and recompile the EA. That will reinitialize the EA on MetaTrader, and all symbols in your current list MetaTrader will begin publishing bid-ask information for them as it comes in to any subscribing parties. And then you can subscribe to any new symbols you've added to that list here via the MTX subscribe functions. So this was a recap of the demonstration we did last time. You're encouraged to use a dedicated terminal for setting up a price feed server. That way you can in fact connect to 2 different terminals via 2 different subscription ports or push and pull ports, depending on what you've configured them to be for trade execution, reporting and management, and different subscription ports for market data subscription. The next part of this segment focuses on MetaTrader's HST file format, which is a proprietary format in which MetaTrader stores pricing data for every symbol, and every symbol by every time frame you've ever selected on a chart. So for instance, if you've selected 3 different time frames, the 5-minute, 60-minute, and daily time frame on the euro-dollar chart, for instance, for each of those time frames, there will be a euro-dollar that time frame HST file stored inside MetaTrader's root history folder. The objective here is to ascertain what the best way is to go about extracting historical data from MetaTrader. Is it ZeroMQ or is it flat file reads? In the case of ZeroMQ, the functionality is already available in the script, in Python script. Go ahead and look through the code when you have a moment, and you'll see that there is a subscribe market data request function that sends a request over the network to your MetaTrader instance if it's running the ZeroMQ server EA, and requests data with a start and end timestamp which MetaTrader parses and returns to you data using MetaTrader's internal functions. And that's it. Now, depending on the size of the data requested, you may encounter certain challenges. How efficient does it become the case to request data over ZeroMQ, and are there any alternatives to doing so if it's historical data we need? In the case of live market subscription, that's a different case altogether, because that data in most cases will not be present in the HST file, as they do not update by the tick. But in the case of historical data, there is an argument for extracting data directly from the HST archive as opposed to sending requests over the network via ZeroMQ. Both functionalities exist for your convenience. However, the faster approach, given that especially in cases where the Python script and the MetaTrader terminal are both on the same host machine, there is an argument for reading flat files as the more efficient approach to getting the data, getting the historical data. There is a challenge there, however, and that challenge is that, well, what do you do in cases where you need data within a certain range of timestamps? That's a subject we'll cover in the next segment of this series, but we'll touch on it today and run through the challenges once we've gone through a bit more about what the HST file format is and what it looks like from a programmer's perspective, and how in fact how simple it really is to go ahead and do lookups on the HST archives. Let's describe in a little bit of detail on what the HST archive actually looks like from a programmer's perspective, and then run through some code in Python on how to read the HST archive in Python and extract information from it. Perhaps the best way to understand, to demystify the HST file format phenomenon, is to visualize what it actually looks like from a programmer's perspective, from an algorithmic trader's perspective. If you wanted to read data from the HST archives inside the MetaTrader history, root history folder, how would you go about doing that? You'd have to know what the HST structure actually looks like for you to be able to read it. We know that it's a binary format, but do we know the structure? So the first thing to understand about an HST archive is that it is composed of two main chunks, and that first chunk is the header, which contains information such as the copyright information, the time frame, the period, the symbol for which this HST archive is for, the last time it was synchronized with data coming into MetaTrader, etc., things like that. And that header is 148 bytes long. This would be a good time to take out your notebook and write these things down just for future reference. Anything that's followed after the header are bars, structures containing bar information, and each bar is 60 bytes long, right? So an HST file at the end of the day is a box that contains two main kinds of things. The first being the header, which is at the very beginning of the file, and any structures found after the header, if they are 60 bytes long, which they will be, then they constitute bar structures. Now, I told you already that the header contains information that is specific to the HST archive we're examining. So for example, and we'll go through this in Python code shortly. I'll show you how to write the code for it. We've already written it. We'll publish it to GitHub for you, but we'll describe this in more detail by looking at code as well. But it's important that we go through this definition here first. Now, the header contains information about the symbol, the synchronization, etc. that we just discussed. What does the bar contain? So each bar object, let's just draw a little line here. Each bar object is composed of a few things. It's 60 bytes long, and we'll go through how those bytes are constructed. So that as an algorithmic trader or an algorithmic developer or quant developer, you can understand how each bar component works, how it is put in place, and then read those into your respective environments accordingly. Each bar object is composed of the following information. You have an open timestamp, the open time of the bar in MetaTrader terms, followed by the open price, then the high price of that bar, the low price of that bar, the close price, the volume, spread, and something called real volume that is only available for certain assets. So this is the main, these are the main components of a bar object. It's composed of 8 objects, 1, 2, 3, 4. Let's label them so it makes things a little clearer. All the way from B0 through to B7. These being 1, 2, 3, 4, 5, 6, 7, 8 objects, 0 through to 7. Now, each of these fields has a certain size. Remember that the full size of a bar object is 60 bytes. So their data types dictate the size of each field in the bar object. So open time is 8 bytes. Again, open price, these are doubles. So this is an unsigned long. This open price is a double, and high is a double, low is a double, close is a double, volume is also a double. Spread is a 4-byte integer, and real volume is also a double. So that is 8, 16, 24, 32, 40, 48, 52, 60 in total. That's how the 60-byte array is structured. So moral of this brief introduction to the HST archive, it is the summary of this is that an HST archive is composed of 2 main chunks. The first being the header, which is 148 bytes long, and any data subsequently is composed of bar objects, each of which is 60 bytes in total. And of those 60 bytes, these are the respective bytes of the parts contained inside any bar object. So at the end of the day, if we want to extract information from an HST archive, we need to iterate over bars contained inside the HST archive. The next problem is that HST is a binary format. So we need to be able to parse this, unpack these structures accordingly. What do we do for that? In Python, we can use the struct module to achieve this. I've opened up the Struct module page for us just to go through some brief information about why we're considering Struct for this. Struct is a module that performs conversions between Python values and C structs represented as Python strings. Now, by default, the result of packing a given C struct includes pad bytes in order to maintain proper alignment to C types involved, etc. We don't have to worry about this too much. We'll be using our system's byte order and specifying the indexes ourselves, since we know the structure beforehand. We know what it looks like, as we saw on the whiteboard earlier with our 60-byte array, the open time, open, high, low, close, volume, spread, real volume array of data. Now, this particular module struct can be used in handling binary data stored in files or via network connection. So there are other use cases that we can explore in future should we want to go over the network, say requesting data from an HST archive sitting on a remote machine. There are those use cases that can come to life with struct as well. It uses format strings. I won't bore you with going through all the format strings. I'll simply pick out the ones that we need, explain to you why we're using them, and how they fit into the whole picture. So for that, let's head back to my Python environment where we can implement this in code and then get data from MetaTrader on demand from the HST archive. We're in my Python IDE. Here I've written the class for you. It's been written separately, but feel free to incorporate it into the ZeroMQ-Connector code that you already have, or use it independently. It's completely as you wish. So the first thing you'll notice is that I've talked about the format again here. So the HST file format is valid as of MetaTrader version 5.7.4. And for more details, you can visit this link. This code will be available on GitHub as soon as this video is available for you to watch. As I mentioned on the whiteboard, the database header is 148 bytes long. It contains version, copyright symbol, period, digits, time sign, last synchronization, and 52 bytes of unused stuff that I believe MetaTrader plans to use at a later date. Just haven't used it now, and for some reason I've reserved the space for it. Anyway, we won't be looking at the header other than skipping over it. for our purposes. The bar structure, as I described on the whiteboard, is 60 bytes long. The first CTM value is your open time. It's a datetime object that will transform into an unsigned long that will transform into a Python integer, datetime being considered a C type of unsigned long. Open, high, low, close, and volume are type double, which is a Python type float. An integer value spread is 4 bytes long, and it is simply a conversion straight through from integer to integer in Python terms, 4 bytes in total. And again, long real volume will be considered an 8-byte object as well, and read accordingly. So in order for us to do that, we have to come up with a format string. The format strings necessary here, I've taken out of the Struct module page for us. Q refers to, as I was mentioning earlier, the unsigned long, which is a Python type integer of size 8 bytes. The D refers to the double objects. So we have open, high, low, close, and volume. Open, high, low, and close are doubles. Then we have volume, which is a long object, and Q is the format string required for interpreting a long into a Python integer. And then I, which is the format string for interpreting a C-type integer to a Python type integer. And finally, Q again for interpreting a C-type long to a Python type integer. The little arrow at the beginning specifies byte order. So this is something we can go through very quickly here. Here, the arrow pointing to the left specifies little endian. And how I came up with that was I imported sys, and the sys module has a function called byte order, and that simply tells you what byte order resides on your machine. So here, in my case, it's little endian, and little endian corresponds with the left arrow here. So you must put the left arrow, the byte order, before the format strings that you require in order to parse your bar structure. And that's already been done for you. So that was a little tutorial on struct and format strings and how that applies here. We're almost done. So what we've done here now is come up with, we've specified the header bytes to skip, which is 148, the bar bytes to iterate over, which is 60 bytes to the bar. And from here on, the code essentially skips over the header bytes, does a file seek. For each bar, it unpacks the data using the format we've provided, the HST byte format we've specified in format strings up here, and unpacks everything into its respective lists that we have set up over here. You have time later on to go through the code. This is fairly simple to understand. If you have any questions, of course, feel free to open an issue or comment below this video on YouTube or elsewhere where you see an opportunity or a place for interacting with us. And that's simply it. For every 60 byte structure found in the file after skipping over the header, struct in Python unpacks those bytes into their respective values. Those values are stored in a list, and that a list for each value type, and then those lists are combined into a data frame later on and returned by the function. To demonstrate how this works, we'll quickly just load this class and create ourselves an object. Let's call it empty, and empty equals DWX-ZeroMQ-Connector. Empty history.io is the name of the file. Now that we've created this, we need to execute this function and provide some parameters. By default, I've included the file name that corresponds with the that is essentially generic and is inside my Darwinex live history subfolder. The two brace segments over here, the placeholders, allow me to insert my symbol and the time frame of choice. In my case, I'd like to pull data by default. I would like to pull data for EURUSD on the 60 time frame. The file format, the file name there would be EURUSD 60. So I'll leave those as is, and I'll simply provide the verbose function because I'd like to see how that output looks. Empty underscore run, and we'll simply change the verbosity to true. The default file will be looking for EURUSD 60, which is the HST archive containing 60-minute bars for the EURUSD in my Darwinex live subfolder. And that's it. You'll notice that it's found the file, it's iterating through all the bars it's found in the file, which are 131,862 price bars. And once it's completed those, we'll have the data available for ourselves to manipulate. You can save it as a CSV, you can do anything with it really. In the next segment of this tutorial, we'll take a look at how to do efficient lookups on HST archives. We don't want to load, as you can see right now, we don't want to load the entire file every time we want to do a historic lookup. So here is the output. The function finally takes all the lists and creates a data frame out of them from the dictionary we compile. And here we have transformed a binary HST file into a pandas data frame containing all the data available inside the HST. And as you can see, the spread and real volume columns have 0 in them. These values are usually populated only for a fairly select few assets. So generally for our purposes in future segments in this series, we're going to ignore spread and real volume and just pull the first 5, which are open, high, low, close, volume, and of course the timestamp. And this is how you load an HST file into your pandas, into your Python environment. As long as you understand the structure of an HST archive, it is in fact very simple to parse an HST archive. In the next segment, we'll also be going through the FXT archive format, which is MetaTrader's backtester, which is the format data is stored in for MetaTrader backtesting. And we'll go through discussing a few things such as the quality of MetaTrader backtesting that affects the sleep of so many traders, 90% versus 99%, et cetera, et cetera, et cetera. We'll be addressing all those concerns and providing a clear answer on what modeling quality actually means in a backtesting context, and whether the 90 and 99% that you see in MetaTrader backtesting actually reflect the quality of the data, or are they hard-coded values? That will become known in the next segment, but for now, we're going to stop it here. And hopefully today we have learned a few things. We have learned how to set up a market price server via ZeroMQ using Python and MetaTrader. We've attempted to demystify the HST file format. We've learned that it's a binary format. We've learned that in Python we can use the struct module to unpack the byte structures each bar holds into their constituent components, those being open time, open high, low, close, volume, spread, and real volume. We learned that the HST file is essentially a structure composed of a header and bar objects, and each bar is 60 bytes long, while the header of 148 bytes can essentially be skipped for our purposes when we're dealing with just prices. We talked about some concerns. As you just saw, when we were pulling information from the HST archive, it can be a fairly lengthy process. And you don't necessarily want to pull the entire file every time you want to do a history data lookup. So there are certain numeric approaches, a mathematical approach to go ahead and do a price lookup from an HST archive that we will discuss in future segments of this series. But for now, that was just a little introduction to the challenges that come about as a result of considering reading data from HST archives as opposed to requesting it over the network via ZeroMQ. Both have their pros and cons. Hopefully this description shed light on both of them, and more importantly taught you how to both look at an HST file in terms of its formatting, and secondly how to retrieve data much faster than other options will enable directly via HST file lookups. Thank you for watching, and see you next time.